Hello, welcome back for lesson 3.4. We're going to work on putting probability into another form, and we're going to use what's called a contingency table to do that. So let me get my screen shared here. A contingency table provides a way of portraying data that can facilitate calculating probabilities. The table helps in determining conditional probabilities quite easily. The table displays sample values in relation to two different variables that may be dependent or contingent on one another. So, an example here says, suppose a study of speeding violations and drivers who use cell phones produce the following fictional data. So in the columns, we have speeding violation in the last year, and the other column is they did not have a speeding violation in the last year. And then in the rows, we have they use a cell phone while driving and they do not use a cell phone while driving. And altogether, there were 755 people. That's down here in the right corner. So the total number of people in the sample is 755. The row totals are 305 and 450. So there were a total of 305 people that said they use a cell phone while driving. Calculate the following probabilities using the table. So we have first probability that we want to calculate says, find the probability that the driver is a cell phone user. Driver is a cell phone user. So that's all we need is a cell phone user. Uses cell phone while driving. 305 of them. So 305 out of the 755. So we put that in our calculator, 305 divided by 755, we get 0.404, which is approximately 40.4%. Now, find the probability the driver had no violation in the last year. Okay, no speeding violation in the last year. We're looking at all of those people. So 685 out of the 755 is 0.907, so approximately 90.7% did not have a speeding violation last year. That's good. C says, find the probability that the driver had no violation in the last year and was a cell phone user. So and means they both have to happen. So no violation and they're a cell phone user. So that would be this group and this group where they overlap, because they have to be both. So that would be the 280 people. They had a cell phone, they use a cell phone while they're driving, and they had no violation. So 280 out of the 755. Is 0.371, so approximately 37.1%. We're both. Okay. Now it says, D, here, so find the probability that the driver is a cell phone user or had no violation in the last year. So now or, okay. So that means we have the probability of the cell plus the probability of no violation minus the overlap, which is the probability of both, which we just found in the last part. So the probability of a cell phone was the 305 plus the people that had no violation was the 685 minus the 280 people that overlap. Okay, all over the 755. Now we could just use the decimals that we found before, but this is the raw data. So 305 plus 685 minus 280 is 710 out of 755. So 94%. So remember, when it's an or, you have to check for the overlap. Find the probability the driver is a cell phone user given the driver had a violation in the last year. Okay, so this is a little bit different. So this is the probability that cell given violation. I'm just kind of shortening it. So this is the probability of cell and violation divided by the probability of violation. So cell and violation is they use a cell phone and they got a violation. So that would be the 25. They got a violation and they use a cell phone. So that would be 25 out of 755, 25 out of 755 over just the violation. Would be the 70. And when we take the fraction divided by the fraction, we get 25 out of 70 is 35.7%. Okay. And the cool thing is you could, because it's in a table form, you could say, given that they had a violation, so just out of these people, what percentage uses cell phones? That would be the 25 out of 70. So that's the cool thing when it's in a table form, you don't always have to set it up in the proper formula. So F says, find the probability that the driver had no violation last year, given the driver was not a cell phone user. Okay, so probability no violation given not cell. So let's just look here. So not a cell phone user. So of these 450, we want to know that who had no violation. So of the 450, it was 405. And let's go back and do it the formal way and we'll see. So this is the probability of no violation and no cell divided by no cell. So the no violation and no cell phone, let's look at that. No violation and no cell phone is the 450. I'm sorry, the 405 was the overlap. 405 over 755 over probability of no cell phone is the 450. So we were correct. And this comes out to be 90%. So the contingency table, when it's set up and created, or if you have information to create it, it really makes things easier to use. The table below shows the number of athletes who stretched before exercising and how many had injuries within the last year. So injury in the last year versus no injury are the column values, and the row values are they stretch and they do not stretch. So what is the probability that the athlete stretches before exercising? So stretches would be all of these 350 out of the total 800. So 0.4375. 43.75%. What is the probability athlete stretches before exercising and given there's no injury in the last year? So Because we have it on the table, we can just go straight to those that have no injury in the last year. So of the 514, what is the probability that the athlete stretches? So the athlete stretches, of those 514, 295 of them stretch. So the table definitely helps with the contingency probabilities. Okay. This one says, the table below shows a random sample of 200 cyclists and the routes they prefer. Let M be the males and H be the hilly path. So they take either the lake path, the hilly path, or the wooded path, and then either they're female or male. So out of the males, so this would be a contingency. So out of the males, so out of 90, what is the probability that the cyclist prefers a hilly path? So this is the probability of hilly given they're a male. So out of the 90 males, the hilly path people are 52. So 0.578, which is about 57.8%. Are the events being male and preferring the hilly path independent events? That's a good question. And if they are independent, then, right, the probability of male times just the probability of hilly. So we went over this in the last chapter. So they would be the same as the probability of the and, right, which would be male and hilly. So the probability of just being male is 90 out of, oh, this should be 200 right here. 71, 90 plus 39. Oh, that should be a 200. So it should be, the male would be 90 out of 200 times the hilly would be 90 out of 200. Which would be 0.2025. The probability of male and hilly would be male and hilly is the 52 out of the 200. And that comes out to be 0.26. So those are not equal, so they are not independent. So that must be true for them to be independent events. So let's look at the next few triad here. This table here relates the weights and heights of a group of individuals participating in an observational study. So we've got their height is tall, medium, or short, and then their weight is obese, normal, or underweight. And find the total up for each row and column. So we're going to go ahead and fill in these. There are 50 in there. And that should be 104. And that should be 51. And then we're gonna do our row totals. And so our row totals of 66 plus, no, 60 plus 99 plus 46 is 205. And we have to make sure the column totals add the same, 50 plus 104. Okay. So questions we're going to answer about this. 200 people. Find the probability that a randomly chosen individual from this group is tall. So we just want to know the probability of tall. So tall would be the 50 people out of the 205. So that would be 24.4% rounded to 1 decimal. Find the probability that a randomly chosen individual from this group is obese and tall. So and means they have to be in both. So the probability of obese and tall. So obese is this row and tall. So this overlapping cell right here of 18 people out of the 205 is a 0.0878, and that will be about 8.8% are obese and tall. Find the probability that a randomly chosen individual from this group is tall, given that the individual is obese. Okay, so because it's in a table, we want to know probability that tall given obese. And so we can go to the obese people. So out of the 60 people that are obese, how many are tall? And that would be the 18. So that comes out to be 30%. Next says, find the probability that a randomly chosen individual from this group is obese, given that the individual is tall. So let's see here, probability of obese, given they are tall. So now it's out of the tall people, so 50, how many of them are obese? That same 18. And that's 0.36. So not the same. Find the probability that a randomly chosen individual from this group is tall and underweight. So probability of tall and underweight. So tall and underweight would be the group of 12 individuals out of the 205. And that is 0.0585. So approximately 5.85% are tall and underweight. Are the events obese and tall independent? Okay, obese and tall independent. So if they were independent, then the probability of obese times the probability of tall would be equal to the probability of tall and obese. So probability of obese is 60 out of 205 times the probability of tall is 50 out of 205. And then we're questioning if that's equal to the probability of tall and obese. And that is 18 out of 205. So we can, that's really multiplying. So we've got 60 divided by 20. So I'm going to multiply here 60 times 50. 60 times 50. Divided by 205. So probably obese times tall is equal to 0.0714. And we're question mark, is that equal to obese and tall? And that's 0.0878. So no, they are not independent. They are definitely dependent. So hopefully that helps your understanding of probability a little bit more using contingency tables, and catch me back for lesson 3.4.